All right, let's dive in. There's this massive, kind of invisible shift happening in the world of AI. And no, it's not about some new, smarter algorithm. It's about something way more physical. We're talking about a race to stop the most powerful computers on the planet from literally melting down. And the solution? It all comes down to liquid cooling.
So, here's the situation. We're in 2026, and AI's incredible progress, well, it's about to slam into a wall. A very real, physical barrier. The chips that power our AI models are just so powerful now, they're generating an insane amount of heat. So much heat, in fact, that the way we've always cooled computers is about to completely fail. We've officially hit what's being called a thermal wall.
And that brings us to this number, 50 kilowatts. Now, why does this matter? Well, this is the magic number, the absolute red line. It's the power limit for a single server rack when our old methods, basically giant fans, just stop working. It becomes physically impossible. You literally can't push enough air through the system fast enough to keep the hardware from frying itself. Game over for air cooling.
So this is what we mean by the AI thermal wall. Just think about this for a second. Some of the latest AI chips are cranking out over 1,000 watts of power each. Trying to cool that with just air? That's like trying to put out a bonfire with one of those little handheld fans. It's just not going to happen. We've hit the absolute physical limit of what the air we breathe can do.
Okay, so what's the answer? How do we get past this wall? Well, it's liquid cooling. And this isn't some weird niche experiment anymore. It has become the absolute standard for any new AI data center going up today. It's really the only way forward. The whole idea is to use special liquids, instead of air, to pull all that crazy heat away from the components.
And just look at this chart to see why this is such a big deal. The difference is, well, it's dramatic. If we give air a score of 1 for how well it transfers heat, liquid gets a score of up to 3,500. Yeah, we're not talking about a small improvement here. This is a total game changer. It's just on another level. And that right there is why the entire industry is scrambling to make the switch.
All right, so we get why we need it. But how does this stuff actually work? I mean, what does it look like in practice? Turns out there are two main ways to do it, and they're pretty different from each other.
Okay, the two big methods on the table are direct-to-chip and immersion cooling. The names are pretty descriptive, actually. You can think of direct-to-chip as a really targeted approach, almost like a tiny little radiator that sits right on the chip itself. Immersion cooling, though, that's the wild one. It's exactly what it sounds like. You take the entire server and just dunk it in a high-tech bath.
So let's look at direct-to-chip first. Here's how it works. You have this metal thing called a cold plate, and it sits directly on top of the super hot AI chip. Inside that plate are these tiny little channels. Cool liquid gets pumped through those channels, and as it passes, it just sucks the heat right out of the chip. Then, that now warm liquid gets pumped away to a radiator to get cooled down again, and the whole cycle just keeps repeating. It's super targeted and really, really efficient.
Now, immersion cooling is a whole different beast. This one is all about total submersion. You literally lower an entire server into a tank filled with this special liquid. It's a dielectric fluid, which is just a fancy way of saying it doesn't conduct electricity. So, no worries about short-circuiting everything. The beauty of this is that the fluid is touching everything at once, cooling every single component on the board simultaneously. Now, here's where it gets really interesting. A shift this big, it's not just about swapping out some fans for a few pipes. Adopting liquid cooling sets off this huge chain reaction, a cascade of changes that affects everything about how a data center is designed, how it runs, and even the economics behind it.
And you can see that ripple effect right here. Step 1. You bring in liquid cooling. That means you can get rid of those massive, power-hungry air conditioning units. That immediately leads to step 2. You use way less power. Less of your electricity bill is just wasted on cooling overhead. And because the chips are so much cooler, you get to step 3, higher performance. They can run in turbo mode for way longer without throttling. And all of that leads to step 4, you're saving critical resources, both electricity and water. It's a huge win-win-win.
And get this, the impact on just the physical space is absolutely staggering. You're looking at a 75% reduction. Because you don't need all those giant aisles for air to flow or these massive air handling units, you can pack the same amount of AI computing power into a space that's a quarter of the size. When you're talking about building these incredibly expensive facilities, that is a massive, massive advantage.
So what's it actually like inside one of these new data centers? Well, for starters, the whole cost structure is different. It costs more to build up front, sure, but your monthly electricity bills plummet. And then there's the sound. It's quiet.
The deafening roar of thousands of fans is just gone. Instead, you just hear this quiet hum of pumps. And finally, the jobs are changing. The technicians working there aren't just changing air filters anymore. They're basically plumbers and chemists, managing fluid levels and plumbing systems.
But of course, it's not all sunshine and roses. A massive technological shift like this never comes without its own set of challenges. And yeah, while liquid cooling is absolutely the necessary next step, it also brings a whole new set of rules and, you guessed it, a whole new set of risks to the table.
And this table really lays out the trade-offs pretty clearly. On one side, you have some serious upfront challenges. I mean, it can cost 40 to 60% more just to build the place. The racks themselves are way heavier, so you need stronger floors, and of course there's always the risk of a fluid leak. But then you look at the other side, the long-term gains, lower energy bills, higher and more consistent AI performance, and packing more power into less space. The bottom line is the industry has looked at this and decided the gains are so huge, these challenges are absolutely worth tackling.
So that kind of leaves us with one last big question to think about. As our world becomes more and more run by AI, we have to realize that its progress isn't just about clever code and massive data sets anymore. Now it literally depends on pumps and pipes and, well, fluids. So what does it mean for our digital future when the next great leap forward really depends on something as down-to-earth as plumbing?